Hi folks, welcome to the next lecture. And in this lecture we're just going to take a look at simple log functions and how we solve them. So how do we recognize a log function? Well, first of all, just to define a log again, when we see the word log, that automatically means log to the base 10. It doesn't mean anything else. And similarly, if we see the word ln, the logarithmic natural, that's log to the base e. And again, there's no other interpretation of it. So log is log to the base 10. So all of these now are logarithmic functions. Even though they look completely different, they're all defined by the log term. Simplest equation, y is equal to log x or ln x. And the general equation, a log bx. To see where we are in the grand scheme of things, we're now at log functions. We've looked at all the ones above. We've exponential functions and then analysis of functions to come. Simple equation, general equation, typical graph of a log curve. You should be able to sketch that. Note it's here when x is 1, our output is 0. So for every positive input value, an output value exists. So it's not continuous because the graph does not exist for 0. When x is 0, you can't get the log, and for any negative value. We'll discuss this more later in the lecture. The output grows slowly for large changes in input. This is why it's used a lot for these logarithmic scales. Log functions appear in lots of other scenarios. There's a new formula now describing the age of a dog in human years, which is a logarithmic function as well. So now we're just going to take a look at the equivalence between a power statement and the equivalent log statement. So on the left we have a power statement, on the right we have a log statement. And we can see when we get the log of a big number, so this is our inputs here, when we get the log of them, the values are greatly compressed. And this is one of the features. This is what we'll use logs for a bit. Sorry, it's a little bit out of sequence, but the idea is still the same. I don't know why that's happened. It shouldn't have happened. I spent ages getting those to look equal. But the main thing here is a number. Like here we have 10 billion. When we get the log of that, it's simply reduced down to 10. So logs are very good for compressing large ranges of values, and that's what they're used for when we look at the Richter scale, the decibel scale, the pH scale. That's one of their principal properties. Now we're going to take a look at the graph of log x just in a little bit of detail, and it's taken the information we got from the previous slide. It's not to scale, so it's just to give us a general idea. So the log of 1 is 0. So our input is 1, our output is 0. The log of 10 is 1. You can go back to the previous slide to see where these are. Log of 100. Remember, 100 could be written as 10 squared and the logs will cancel out. The log of 1,000 is 3. The log of 10,000 is 4. The log of 100,000 is 5. The log of 1,000,000 is 6. The log of 10 million is 7. So we can see the input is rising very rapidly, but our output, the y value, is only rising gradually. And now we're going to take a look here. This is very important. So this graph here describes the decibel scale and the Richter scale, because they're dealing with values greater than 1. Movement of the earth for Richter and sound pressure for decibel. We're now going to zoom in and take a look at what's happening between 0 and 1, because this is this is where the pH scale lives. So now we have 1 on the right and we have 0 on the left. First thing, log can't be defined for 0, but we're going to take a look at what happens as we let x get very, very close to 0. So we're going to start examining what happens to our output as we let x get smaller and smaller. Again, it's not to scale. The log of 1 is 0. This is kind of the crossover point with the previous graph. The log of 1/10 is minus 1. Remember, 0.1 is 10 to the power of. So when we get the log of that, we get minus 1. The log of 100th is minus 2. The log of 1,000th is minus 3. The log of 1/10,000 minus 4. The log of 100,000 is minus 5. The log of a millionth is minus 6. So we can see this is the curve then between 0 and 1. And the two curves link up. It's hard to show both of them on the one graph because the x values get so big. The gap between 0 and 1 is very hard to describe. But here's the log curve between 0 and 1,000. And here it is between 0 and 10,000. Now again, between 0 and 1, that detail I showed on the previous slide is still going on. So really the curve is actually coming down like this, but it never touches 0. It's just very hard to show that on a graph like this. This now is just the blue line is the log function and the red line is the natural log function. So they're similar in lots of ways. It's not as easy to describe the natural log function. The natural log of 1,000 isn't a nice easy number like 3. We can see it's a little bit more than 5. But we use our calculator to generate these. Just some common features. Again, we can't get the log of a negative number. We can't get the log or the natural log of 0. So our values have to be positive and greater than 0. Both of them here, when x is 1, they both return an output of 0. So when x is 1, either the natural log of x or the log of x is both 1. And then as x gets bigger and bigger, our outputs grow. So as our input grows very quickly, our output grows much more slowly. So this is just all of that written down in words, not defined for negative inputs or for when x is 0. As x increases, they both increase, log and natural log. Between 0 and 1, this is where I described the values. Our output values increase negatively. So the closer we get to 0, then the more and more negative our output is. Our y value is negative. Between 0 and 1, when you get the log of a number between 0 and 1, your answer will always be negative. The closer it is to 0, the more negative, the bigger negative number you will return. And that's just that there. So now we're going to take a look. We've looked at this last semester, but it's just really a quick review. We're hopefully getting familiar with our operators and our inverses. These are what we were dealing with last week, sine and cos and their inverses. And in the same way, 10 to the power of x and e to the power of x also have their inverse operators. And we've discussed these before. Remember, log is log to the base 10, ln is log to the base e. And there, if we need to kill 10 to the power of, if we need to kill this bit, we use a log with the same base. If we need to kill this, we use natural log, or log with the same base. It's just called the natural log. So we'll take a look at a few examples. So here, convert this power expression into a log. Well, we want to get rid of the power. We want to remove the base, really. We want to kind of change this power statement on the left into just a simple value. So we need to remove the base. To do that, we're going to get a log, but it must have the same base. So we get log to the base 3 of both sides. And here now, log to the base 3 and 3 to the power of, their inverse functions. We saw that from the previous slide. The 2 just drops down. And now we have a log statement. Similarly, again, this is a power statement. We want to change it into a log statement, so we need to remove the base. We need to kill this base of 5. So we use a log with the same base. We apply this to both sides. I'll just rub this out. And then these cancel each other out, and we now have our log statement. So next slide is just questions for you guys to have a go at. Now usually these are the bases we'll only be working in, 10 and E. The previous examples, we won't really be doing any maths with log to the base 3 or log to the base 5. I just used those as examples, but these are 2 for you to try. And now we'll go the other way, going from logs into powers. So here we have a log statement, and we want to kill this. So how we do it is we raise both sides as a power, but we must have the same base. So our log is a base of 3, so our power. And now this looks a little bit odd. We raise the right hand side as a power on 3 and the left hand side. And now these cancel each other out. They're inverse functions. It looks odd. Normally you wouldn't write that line, but it's just to... And finally, we just write our power statement on the left. So both of these statements are saying the exact same thing. It's just one is in the language of logs and the second is in the language of powers. Similar. So again, we want to get rid of the log. It's got a base of 2, so we raise both sides as a power on 2. So we have log to the base 2 of 32. These cancel each other out. Once we remove the base, the 32, the power just drops down to become a normal value. And finally, we just write our power statement on the left. So, in a similar fashion, here's 2 for you guys to try. Again, pause the video, give these a go. Remember, ln is log to the base e, so that's your clue as to which base you're going to use. And now we'll start to solve equations. So we didn't get this far last semester because we didn't have our calculators, but we use this skill now to start solving out functions. So I want to get x on its own. I want to kill this base of 10. So the same as before, I get log to the base 10 of both sides. Now I could just write log. I just got to get the log of both sides, because that does mean, by definition, to the base 10. Just make it look a little bit neater. And now on the left, these cancel each other out. And now you can just get your calculator. First of all, I suspect my answer is going to be negative because the value is between 0 and 1. Remember what I was saying? The log of any number between 0 and 1 is going to be negative. And x is equal to minus 0.4318, we'll say. Okay, it goes on, but 4 decimal places should be loads. Here's another example. Now really, just to be clear, I'll just write this out with the base that's logged. So this now at least shows us what we need to do. I want to get rid of the log. It's got a base of e. So I'm going to raise both sides as a power on e. Now, once you get used to it, guys, you don't need to write this intermediate step. It's kind of, this only appears momentarily. These cancel each other out. And we get x is equal to e to the power of 0.5. And now we just get our calculators. And we get x is equal to 1.64872. And again, it goes on forever. Well, it goes on for a very long time anyway. It goes on beyond my calculator's ability to compute it. So now, in a similar fashion, here's some ones for you guys to try. So again, just pause the video, give those a go. And now we'll start to kind of solve more complex functions, but the same principles apply. Now we have two things. We want to get x on its own, but there's two things acting on it. There's the log and there's the 3. You always work from the outside in. So I want to kill the log first. So to kill the log, it's log to the base 10. I raise both sides as a power on 10. So when I do that, you can kind of speed things up a little bit. When I raise both sides as a power on 10, well, on the right hand side, this is what happens. On the left hand side, when I raise it to a power on 10, that just kills the log. So this would be a more normal way to write it without writing the intermediate step. Now, don't get your calculator just yet, because if you get the calculator and try and compute this, your calculator is going to round off your answer. But then we're going to have to divide our answer by 3, which is what I'm doing now. I want to get the... So it's much better to just leave the problem like this. And once you have x on its own, now you can compute. So, 10 to the power of 0.75. Be careful to move the cursor properly. Don't divide it by 3. And here we get 1.87447. We'll just say 45. So it's the exact same as solving functions, solving equations from before. We want to get x on its own. You work from the outside in. But now we're just going to be kind of killing logs or killing powers as part of the process. Slightly more complex problem. Again, now I've got several things acting. The log is going to be the first to go, then the 4, and then the 2. Remember, always work from the outside in. Remove the furthest thing away first. So to get rid of the log, we're going to raise both sides as a power on 10. Now when I raise the left hand side as a power on 10, that kills my log because they're inverse functions. So now we've got 2x plus 4 is equal to this. Now I can't get rid of that 2 first because the 4 is kind of in the way. If I wanted to divide by 2, I'd have to divide everything by 2 first of all. So I move the 4 first. I subtract 4 from both sides. Minus 4. And again, I know you're tempted to dive for your calculator, but try and keep the problem intact until you get to the very end, and this minimizes. So we want to get x on its own, so we're going to divide both sides by 2. And now we reach for the calculator. Again, be careful to move the cursor so you're not writing 10 to the power of 1.1 minus 4. It's 10 to the power of 1.1, kind of, and then subtract 4 from my answer. And divide by 2. So we now get x is equal to 4 0.2946. I'm just going to double check that just to make sure I haven't made a mistake. Yeah, that looks right. Yep, so there's our answer. Have I rounded correctly? Yeah. Now one more. Now this looks quite difficult, but it's the same again. Look, x is here. So we just start at the left. So x is kind of on the right hand side of the term. So get rid of the 2, get rid of the log, get rid of the 7, get rid of the minus, and then get rid of the 3. Now sometimes people are tempted to use the log laws and bring that 2 up as a squared. But you haven't actually moved it away from the left hand side. You're just actually making your life an awful lot more difficult. The 2 is joined on by multiplication. So the easiest way to get rid of it is to divide both sides by 2. And this gives us 1.75 divided by 2. Next step, I want to get rid of the natural log. That's log to the base e. So I raise both sides as a power on e. So on the right hand side, now there's no harm in dividing 1.75 by 2 because the calculator will do that. There's no rounding or anything. This is 0.875. Sorry, I'll just work that out. It's just I don't want the problem looking too messy, and I know dividing by 2 isn't going to produce a never-ending decimal, so there's no rounding error. So all I've done there is divided the right-hand side, and now I raise both sides as a power on e. Sorry, I'll move this down. So when I raise the left-hand side as a power on e, that kills the log term. So the natural log disappears and the brackets are opened out. On the right hand side, now we want to move the 7, so we're going to subtract 7 from both sides. E to the power is 0.875 minus 7. Now this is minus 3x. And finally, I want to get x on its own. Now you can move the minus across in one go, but I'm going to just divide both sides by minus 3. So we now get x is equal to e to the power of 0.875 minus 7, all divided by 3. So when we work this out, 875 minus 7 when we divide by minus 3. So that will give us x is equal to 1.5337. And that's our answer. So I hope it makes sense, guys. It's really the same as just solving a normal equation, but we've now got log terms in there to be dealt with. So here's some questions for you to try. Don't be put off. They look complex, but it's the same idea. Work from the outside in. So with this one, get rid of him first, joined on by multiplication. Then get rid of him. It's got a base of e. Then get rid of the 4 with a minus, and then get rid of the minus 2 by division. So take your time, do everything in order, and things should work out correctly for you. So that summarizes kind of just solving simple log functions. In the next lecture, we're going to bring in the laws of logs, which we learnt in semester 1, and the problems will get a little bit more complex. So thanks for listening, guys, and we will chat to you again soon.